All right, so now I've set up a pretty large circuit. At least it's a complex circuit as far as resistor-based circuits go. So I'm going to draw a quick diagram of it. We've got, so if you want to be ultra technical, this side is actually the positive side of the battery, and so we'll have current coming out over here. It'll go through this bulb and then split off into one of three branches. And by that, I mean we've got three branches total, and so our current will split into three branches, not just one of them. I should be more careful. Though we're going to find that that also changes based on what I've got flipped, because at first we're going to start off with only one branch. That being said, we've got current coming out of the battery, goes through this resistor, this light bulb. It can split in three different branches and then comes back over here and goes through this other resistor, light bulb, back into the battery. Now, once again, we've got all of our resistances are the same. In fact, I may actually just erase that, kind of stupid to write it, but just so you've got it actually physically seen there. Here's what we're going to do. I'm going to draw a circuit diagram. I'm going to draw it the way that I'm comfortable with, so I've technically reversed the battery, but it's not going to make a big difference. Okay. So I have this come out. I've got a resistor here. I've got a split that comes down here to a switch. And then joins back over here. We've got another resistor here. I'm going to call this A. I'm going to call this one B. We've got another one over here that comes through here, a resistor, a second resistor, and a switch. I'm going to call this one C and D. And then finally, over here, we've got a switch, and then one resistor, two resistors, three resistors, and it comes back over here. D, we'll call this one E, F, G, and H. Now, this is an extreme case. I don't expect the AP exam to give you this many resistors, but I wanted to show you the same things that we've been learning aren't just for the quote-unquote simple side of the stuff. Especially with a resistor-based circuit, all of the things that we've learned can now go to an arbitrarily large circuit. We can have a bunch of things that we're keeping track of. Now, there are a couple things that I'm going to want to take a look at. We'll call this one branch B. We'll call this one branch C, and we'll call this one branch E, based on the first resistor, so to speak, in that branch. Because one of the things that we haven't done yet that I'd like to take a look at is actually see what happens to the potential differences, the voltages across each of these. Because I know a common mistake that people have is they think that the potential difference stays the same for these whenever we switch stuff out. You've heard me say it before, I will say it again because it's very important that you remember this. When you change one part of the circuit, you're probably going to change everything about the circuit. The only things that don't change are physical properties of the circuit. That being that we've got, say, a 6-volt battery. I've got two battery packs here that'll come up to a total of 6 volts, and the individual resistances of each of the resistors. Those are a physical value. Now, I don't know what the resistances are of these, but they're probably something like maybe 20, 25 ohm. So I could fill those in, but that's not really what I want us to do with this. We could do it. If you check back on the Ohm's Law lab, you'll see that light bulbs are a little bit weird. They don't necessarily have a set resistance, or they don't always play by the rules that we'd like, because they're not always an ohmic resistor. In fact, they're usually not. Ideally, what we would be using are these, the actual ohmic resistors, but I like to use the light bulbs because it can show us the outcome that we want very quickly and easily. Okay, so here's what I'm going to do. Right now, we've got nothing going on with any of these because I've got all of the switches open. This is an open circuit. Real quick, I'm going to check the total potential. Ooh, 5.99 volts. We're pretty much right at 6. Here's what I'm going to do. I'm going to show you that each of these paths is set and ready to go. So if I close this switch, let's predict what's going to happen. So if I close the switch on B, we're going to have a closed circuit so that charges can move, but they cannot move through branch C or E because those will still be open. So I'll have charges that come out of the battery, technically on this side, but they come out of the battery, they go through one of the resistors, go through branch B, go through this resistor, and go through this one. Since there are no junctions where they could split off and go somewhere else, that means that all the current goes through A, all the current goes through B, and all the current goes through H. So they all have the same current, and if they have the same resistance, they should all be the same brightness. Let's check. Here we go. Indeed they are, at least pretty close. All right, so this branch is working fine. I'm going to close this one. Now let's ask the following. And here's one thing that I set up just in case you were wondering about it. I've set this one up where the switch happens first and this one up where the switch happens last. It doesn't make any difference. Let's predict what's going to happen when I close this one. Because again, doesn't matter that the switch is here before this resistor or after this resistor, they're still both doing the same thing. And when I flip it on, instantly all of them come on. When I flip this one on, which we'll do in just a moment, you'll notice that all of them instantly come on. It doesn't matter if the switch is before or after the light bulbs or resistors. All that matters is how these branches are set up, because all of the charges have to flow at once, not just one of them. Remember, it's kind of like musical chairs. There are charges all through this, but they can't move until I close the circuit. All right, now that we've got that reminder done, let's take a look at branch C. Okay, so the charges, let's see, they can't flow right now, but if I close this, we would have a current coming out of the battery, going honestly through the whole circuit all at once, but I'm going to track just one basic charge as it flows through. And it would go through this one, so resistor A. It would go through branch C and only C, so it would go through resistor C, D, and H. Once again, all of them would be in series with no branches going off, so whatever the total current is, all of it will go through A, C, D, and H, which means they should all be the same brightness since they have the same resistance. And indeed, they are. Now, let's double check, because you may be thinking, oh, well then those two are exactly identical. But remember, on this one, I have only one resistor, and on this one I have two. So real quick, let's do a quick comparison. We see that they do about the same thing, but my total resistance for this one is going to be 20 plus 20 plus 20, assuming 20. That's about 60. If they're all the same, then I would have 3 times whatever my resistance is. 3 times 20 is 60. However, in branch C, I've got 2 more. This would be 20, 20, 20, 20. 4 times that would be 80. I have a slightly higher resistance because I have 2 resistors here instead of the 1. So let's quickly compare them. My resistance is lower if I only close B, which means more people are getting out of the gym, if you will. And therefore, A and H, and B for that matter, should be brighter than A would be, or A and H would be if I only have C. So let's check that real quick. So let's look at A. Here is branch B. This one should be brighter. And if we look closely, we can see that this one's a little bit dimmer. So here's branch C. I'm going to close C, so keep an eye on that. I know it can be kind of hard to see in the video, but here we go. It's a little bit brighter. You kind of have to flip it back and forth a little bit to see. Now you can see a fluctuation where it gets brighter for a little bit longer. Part of that is because the way these light bulbs work, they have a little bit of lag time. They take just a moment to get back up and get bright, and then they take a moment from going bright to get dark. It's like when you turn the lights off, sometimes they'll kind of fade a little bit. It's not very long, but it's because these light bulbs work on heating up a filament, and that filament stays warm even after you give them energy. Oops, I'm starting to give away the next part. All right, now that we've got that, let's predict what happens when we close the switch on E. Well, all of the charges are going to go through A. All of them have to go through E, F, G, and H. When I close this switch, I predict that not only will all 5 of these light bulbs be the same brightness because they're getting the same current, they're all getting the same current. The current is different than when it was with B. This has a much higher resistance. 1, 2, 3, 4, 5. There are 5 of these resistors total. So my total resistance for this circuit would be 100. Whereas for just branch B, it was only 60. That's almost twice the resistance, which means we're going to end up with about half the current. So here we go. We expect that all of the bulbs should be the same brightness, but they should all be much dimmer than this. Here we go. They're all about the same brightness, and they are noticeably dimmer than this. Great. So we can start predicting these things. Great. Okay, let's go ahead and turn on branch E again. They're all pretty dim. And let's start predicting what's going to happen when I close branch C. So now I'm opening some more doors. Once again with the gym, when I open this door by closing this switch, a little difficult to keep track of, but that's the terminology. I close this switch. which opens another door. Now we have an additional path here. No longer will the total resistance of the circuit be 100 ohms. We could run through the numbers, and you are welcome to, but it's going to be less than 100 ohms. In fact, it's going to be less than, well, let's see, these two would be 40, and these are 60. So whatever the equivalent resistance of this is, it must be less than 40. So when I close this switch, open the door, that allows more people to get out of the gym, and they all have to go through here and here. So I predict that the current through A is going to go up, and the current through H is going to go up. And since their resistance doesn't change by P, our power, the brightness, equals I squared R, if the current goes up, the power goes up, and these two will get brighter. Now on this one, while we will have more current coming in, it can now split, some of it going this way and some of it going this way. And when you do the numbers on it, you're going to find that the current going through here is actually going to decrease. So what we're going to find is C and D are going to get brighter because they're finally going to get some power, but I predict that E, F, and G are going to get dimmer because now the current is going to split. Some of it goes this way and some of it goes through the new path. A and H are going to get brighter because I'm opening a door, and that means more charges can flow through, more people can get out of the gym, and all of them must go through A and H. So here we go. There we go. These got so dim you might think that they're burned out, but they're not. And these got brighter. In fact, these two are a little bit brighter. I can see a little bit of a light there, but you're probably not going to be able to see it here on the camera, which is totally fine. I can show you that these are indeed not burned out because if I were to remove one of the bulbs, breaking this circuit, we can see that it goes back to these working. So this is actually letting charges through it, even though you're not seeing it. They're not getting enough power for them to give off any light that we can see. I could break this one, and we could see that it goes back this way. So even though these are not obviously on, they are still part of our circuit, and charges are flowing through both sides. Okay? All right, so we did that. Let's keep going. What happens if I open or close this switch, opening yet another door? Well, presumably, we're going to see a repeat of the same thing that we saw here. I've opened another door, which makes it easier overall to get out of the gym, which means our total current is going to go up, and that total current goes through A and H, so both of them are going to get brighter. B will probably get a little bit brighter, and the other ones here are going to get a little bit dimmer because now we have 3 branches that even with the increased current, even less of it will go here, even less of it will go here, and some of it will now be going over here. So let's see. Here we go. There we go. Now, I want you to pay close attention to A. It's kind of hard to see, but here we go. It gets a little bit brighter. Now, at this point, because I'm not reducing the equivalent resistance by that much by opening another door, it's a big deal if I open a second door. It becomes less of a big deal if I open a third door, and by the time you get to opening the 10th door, it's going to have a small effect on these. My equivalent resistance will continue to get lower and lower, but with each of the branches, we're going to have a big step in reduction of the equivalent resistance, and then we end up with less and less of that effect. So if you look closely, it can be kind of hard to see. I'm going to close this switch again. If you watch closely, it gets a little bit brighter. Okay, great. Now let's talk about this because I've told you this and I want to verify it for you. I'm going to get out the voltmeter, and I'm going to show you that the potential difference changes across these. If the current through the resistor changes, which we've already established that it does, by both logic, reason, and what we see, we've got V equals IR. If the resistance of the resistor stays the same, which it does, it's kind of a physical property, or at least for the most part it does. It might fluctuate just a little bit, but not very much. If the current changes, for this equation to hold true, our potential also has to change. So here's what I'm going to do. I'm going to take us back to the original one here. All right, here we go. Set it to voltmeter. What I've got for A, in fact, let's go ahead and do this way. A, B, C, D, E, F, G, H. Okay, so here's what I'm going to do. I'm going to double check the total potential of the circuit now that we've got it connected to a load. It's only 5.65. Now take a look at our next video, internal resistance, to understand why the potential starts to drop as we change different things. But our total, at least for this one, is 5.65 volts, a little bit less than the 6 volts. Now you may be thinking, well, that's because you've had this stuff on for a little while, which I have. But if I turn everything off and I check it, we're at 5.86, a different value. When you connect parts of stuff to real circuits, the potential across the batteries are going to change a little bit. Take a look at the video marked internal resistance to understand why. So I'm going to turn this on. Great. We've got our initial setup here with just branch E going. I'm going to check this. I'm going to check the potential across this. We've got 1.25. 1.25 for A. I'm going to check B. 0. Interesting. Well, that makes sense. There's no current going through it, so the potential drop across it must be 0. Okay. C. Also 0. D. Also 0. 0, 0. Okay, well, those don't have any charges going through them, so great. All right, let's check E. It's about 1.1. Let's check on this one. About 1.1 and about 1.1. So 1.1, 1.1, 1.1, and let's check H and see what we come up with. Hey, look at that, about 1.1. Now, one of the things that we can tell pretty much immediately is, while my light bulbs should be pretty similar, this one might actually be a little bit different because it got a different measurement. Let's double check it real quick. All the rest of them are right at about 1.1. This one's still saying about 1.25. Now, that's probably because this light bulb has a slightly different resistance than the others, but we can see they're all about the same, which means they'd have the same current and so forth. They're the same brightness. All right, great. Here's one of the things that I want to bring up. We haven't really talked about this. Let's say that this is the high end of my battery. This is 0, so we raise it up to a height of 6, and then we go across this resistor, and it drops us by about 1.25. These are still loops. Loop rule, you may be thinking, well, that's a little weird, but shouldn't loop rules still apply to them? Or is it just, it doesn't because, hey, the circuit doesn't work anymore? But we do have stuff here, so let's double check. 6 minus 1.25, that'd be about 4.75, but we know that there's nothing across this light bulb. Let's check something else. I'm going to check across the switch. 3.33. There's a potential across this switch. Now we went from, I was saying 6, but we're at about maybe 5.5 minus 1.25. That would be about 3 3/4 or so, or yeah, no, sorry, about a little over 4. Trying to do this in my head. This is a little bit lower, but there are some other parts in here where it's going to fluctuate a little bit because these are not ideal wires. The biggest thing that I want you to realize is this. There's a potential drop across that switch. Oh, of course, there's more. Yeah, I apologize. I should be drawing out loop rule properly. So I go across the battery and it gives me about 5.65. I go across A and it takes away 1.25. I go across this switch that is open. I'm going to call that delta VS because I don't know what it is, but there is a potential drop across it. I go across B, and B has nothing because there's no current going through it. And I was forgetting H like a fool. I should be drawing out my stuff, and we know that it takes away 1.1. So if I solve for the potential across this switch, because it's not an uncommon question for the AP exam to ask you that, what's the potential across that switch? 5.65 minus 1.25 minus 1.1. My numbers come up to 5.65, what I get from the battery, minus 1.25, the drop on this, minus 1.1, the drop on this. So the missing part is 3.3 volts. And when I check this, I get 3.32 volts. There's our missing potential difference. It's still a loop. And loop rule still applies even though nothing's happening in this part of the circuit. Loop rule has to apply. This is basically a cliff, and one side of it is up high, and one side of it is down low. And if I could close it, then that would change it where this acts as a wire and it wouldn't really have a height difference. And now that lets charges through and the height difference goes to here. In fact, let's check that. Let's go ahead and close this switch. We know that the circuit is going to change. As a brief reminder, we're going to open another door. So that means that we're going to end up with more charges getting out of the battery in a given time. All of them go through A and H. So these two are going to get brighter. These are going to get dimmer as the current gets split. And this one's going to turn on. Bingo. Great. Now let's check our potential differences, though. I told you that everything changes. Let's double check. On top of that, because this is a real battery, our new potential difference is about 5.55 volts. It changed a little bit. Again, check the video on internal resistance to find out why. There's an invisible resistor that we don't see here that's built into the real batteries. Okay, let's double check a few of these things as we go. Now, we said that the current changes through this resistor, so therefore the potential difference, the voltage, must change too. 2.5. 2.5. I'm going to check the potential difference across this switch, and it is about 0.1. So it's not 0, it should be 0, but it turns out that there's going to be a little bit of resistance in this switch in a real-life thing. That's why our numbers don't always work out perfectly. That being said, it should be 0, and over here I've got about 0.7. I'm going to add the potential drop on this one to B, so we're going to call it about 0.8 for this entire branch. In an actual ideal circuit, all of the potential drop would be here, and the switch would have no effect on the circuit. It would just act like a wire. In real life, the way the switch is made, it's offsetting it just a little bit. Okay, so that's 0.8 for this branch total, 0.7 from here and 0.1 from here. I'm going to check H, that's about 2.1. 2.1. Again, a little bit less than A. I think my light bulbs are slightly different. This one's probably got a slightly different resistance than this one. But we can see that they're pretty close to each other, a little above 2. All right, let's check all of these then. E, 0.3. For E, 0.3. 0.3 for F. And finally, G, about 0.25. We're going to round that up to 0.3. The other ones were about 0.27. I'm basically trying to get this to 1, maybe 2 significant figures, make this a bit easier on us. Okay, let's double check our loop rule. Okay, so we've got 5.55. So I go across the batteries, it raises me up to a height of about 5.6-ish. Great. We go across the first resistor, and it lowers us down by a height of 2.5. Great. So now we're at a height of about 3.1. I go across this branch, and it lowers me down 0.8. And then I go across this branch, it brings me down by about 2.1, and I'm left with, instead of 0, about 0.2, but remember we've got a little bit of rounding error in here, so we're pretty close to 0. These are based on real-world things. We've probably got a little bit of a drop in some of these wires, and so we can see that for the most part, the amount we go up is the same as what we go down. I also rounded up 5.55 to 5.6. So 5.6, I'm going to go up this way, go across that resistor. It brings us down by 2.5, so we're at a height of about 3.1. I go down across this, and this drops us down by 0.3. The next one drops us down by 0.3, and the next one drops us down by 0.3, and we're left at a height of about 2.2, which should be about the same height as over here. And then I go across this resistor, and that removes about 2.1. We end up with very close to 0. Given the rounding that I've been doing. Great. So quick question. What's the potential going to be across this light bulb without me changing anything? Just right now, if I were to measure it. What about this one? And what about this switch? Well, we know that this was at a height of about 3 and that this was a height of about 2. So we know that somewhere in this branch we have a potential difference of about 1. This branch was about 0.8, give or take some of my rounding. In fact, I could probably make a better measurement of that. We've got 0.69, so that's 0.7. And this one is 0.15. It might be better for me to call this 0.9. I apologize. Why is that important? Well, this branch is 0.9, and what was this branch? Well, 0.3 plus 0.3 plus 0.3 is 0.9. Remember, might be a little bit off because of my precision of measurement here. But, well, is there any current that's going through resistor C? Well, no, because that branch isn't closed, which means I should have a zero potential across that. Same thing with D, and that means that across this switch, because we need a total drop for this branch to be 0.9, we can guess what we'd end up with. First, I'm going to double check on this. So I'm going to put it here. I look at resistor C, and we end up with 0. Resistor D, also 0. And now across the switch, 0.83. Almost the 0.9. Here's where our potential drops. Basically what it's saying is over here is at a height of 3, down here is at a height of 1. So when I put these here, what it's actually measuring is the height difference between the two. I can check here, and we've got 0.83. All right. Each of these branches has the same potential drop across them. All right, what's going to happen when I close this switch, opening a third path? Well, this one should get a little bit brighter. These should get dimmer, though right now they're getting so little power we can't even see that they're on. This one's barely on, and I'm going to flip the switch. This one went off. It's no longer getting enough power to even light up a little bit. And these got slightly brighter. I'm going to try that again. Give it a moment. Let's take a look at A. Gets a little brighter. All right, so now that I've done that, we've closed this one, and let's double check our total potential across our battery, because this is a real battery. 5.46 volts. We'll call that about 5.5 volts. All right, here we go. Let's double check what happened to our potential across this one. 2.77, we'll call that 2.8. It went up a little bit because the current went up a little bit. But you'll notice there was a big jump between the first one that we added in because that was a huge effect on the circuit. There's a smaller jump, and if I had more branches, we'd probably have a smaller and smaller effect, though it depends on what resistance I put in there. If I continually use the same resistance value R, then we'll have diminishing returns. All right, let's check B. That's 0.2. For B. Let's try C. 0.14, I'm going to call that 0.1, but keep in mind we're rounding a little bit. For D, that's 0.15. I should probably round that up to 0.2, but I'm going to keep it at about 0.1. Let's see what we get on this last one. So E, about 0.1. F, about 0.1, and G, a little bit less than 0.1, but I'm going to round it up to 0.1. I'm going to double check this one real quick. No, that one's right at about 0.2. Let me check this switch. This switch has 0.1 for some reason. So I'm going to add those two together as 0.3. I need to mark this switch. I think it has a problem. Yeah, because this switch is only 0.2. Okay, sorry about that. Camera cut or stopped like it usually does during the long videos. So sorry about that. As I was saying, I think I've just discovered that there might be something a little bit wrong with this switch. I think it's got too much resistance for what a switch should be. So I need to mark this one so I can keep track of it. The other two are significantly lower. That being said, we're going to treat this entire branch as the 0.2 and 0.1. So that gives us 0.3. This one is... Each of these were about 0.15 for C and D, and then each of these are right at about 0.1. So we've got a drop of about 0.3, 0.3 for each of these. All right, finishing this up, about 2.4. All right, let's see how that works out with our loop rule. Once again, you'll notice that H also went up. Went up from 1.1 to 2.1, up to 2.4, just the same as A. All right, so here we go. If I were to do a loop here, I go across the batteries. I'm running out of room here. I'm going to get this out of the way. I go across the batteries, and they give me about 5.5 volts. Then I go across A. It takes away 2.8 volts. And then I go across maybe this branch, which has a total of 0.3, or this branch, which has a total of 0.3, or this branch, which has a total of 0.3. So I'm just going to put in 0.3 for any of the branches. We can save some time on this because we know that the potential drop across each of them is the same. Here, it's 0.3 basically across this one resistor. Here, it's evenly split as 0.5 and 0.5. And here, it is evenly split among the three, 0.1, 0.1, 0.1. Now, one thing that I want to bring up on this is a big part of that is because all of these got evenly split because all of these resistances are the same. If they were different resistances, then the potential difference would change as a result. In fact, they'd be related as a ratio because this has the same current as through there. That's okay. So our branch is 0.3, and then finally we subtract off about 2.4 for H. So this represents any of our individual branches. Let's double check. 5.5 minus 2.8 minus 0.3 minus 2.4 gives us 0. Even with the rounding, we've got it pretty much spot on for 0. Loop rule applies for each and every one of these. All right, so this is how we can work with making predictions on what's going on. Biggest things that I want you to keep in mind. It doesn't matter if the switch is before or after. If the switch is part of that branch, when you flip that switch, it closes off or activates that part of the branch. Nothing can happen. The order on this does not matter. In fact, I can switch these out. Let's see. I'm going to do this. We can see that this one, when I turn this on, it ends up with a potential across it, which is the easier thing to measure. Potential across it of about 2.5. This corresponds with our purple one. Watch what happens. I'm going to close this. I'm going to pop this out. I'm going to switch these out here. I'm going to put this here. I've switched the order on these, and now exact same thing happens, and let's double check. This now has a potential across it of 2.5. This one has a potential across it of 2.1. We're still getting the exact same results. This one has a potential of about 0.66, so about 0.7. And this one has about 0.1 because there's something wrong with this switch. I will get you, switch. All right. And the same thing's going to happen here. I could switch this out with, in fact, let's try this. I'm going to flip this one off. I could put this switch over here at the end instead, and we get the exact same outcome. I could check this. Still 2.5, still 2.1, still 0.3. I could put the switch in the middle of them. In fact, I almost wanted to do this because the switches sit still a lot easier than the light bulbs do down on the little pegboard. This was what I wanted to set the circuit up as in the first place. The switch is now in the middle of them. 2.5, 2.1, 0.3. And if I turn this one off, we can see that they all go back to being dim. I turn this one on. It opens this door. This gets brighter. These two get brighter. This one lightens up just a little bit, and these get dimmer. I could unscrew the light bulb here, breaking this part of the circuit, and it goes back to what it was. The order on these doesn't matter, and the key to that is it doesn't matter that the switch is here or over here. It just matters that it's in this branch, and it will activate or deactivate, open or close this branch based on when you flip it. So order doesn't matter, and the reason for that is it's not just one charge going through and getting stuck somewhere. All of the charges have to move in order for any of the charges to move. All right. Big takeaway from this is, easiest way that I've found to think about what's going to happen with each of these is to go through and think about people getting out of the gym. You're opening and closing doors by adding branches and so forth. So think about that, what it does to the total current and what's happening to that current. All of it has to go through these, but it splits off in these, and therefore you can start drawing conclusions. Your potential differences do not stay the same. For the battery, in our problems, they will stay the same. The only reason that this changed slightly is because in real life, there's a little resistor that's built in here that we're not taking into account. Once again, check the video on internal resistance if you'd like more information on that. If you're in APC, you definitely want to check that. If you're in AP1, it certainly couldn't hurt. I can't remember if they've been asking questions about internal resistance, but it's something useful to take a look at. All right. So this is a complex circuit and looking at what happens when we flip switches. Great.